So we are on 5.1 polynomial functions. So our objectives for this section is to identify polynomial functions and their degree, to graph polynomial functions using transformations, and to identify the real zeros of polynomial functions and their multiplicity. So identifying the polynomial and their degree. Hopefully some of this sounds familiar from previous math classes, but we're going to first start talking about with the monomials that make up polynomials are called its terms. So when you have, for example, if I just have a 2, this is a monomial, right? If I have x plus 2, this is a binomial. If I have x squared plus x plus 2, this is a trinomial. And once I get past that, this is a polynomial. You get that? Okay. They're all polynomials. It's just classified differently. Okay. So when you are classifying them, it's based on their degrees and what their degrees look like. If I have just a constant, then it's a 0-degree polynomial. Okay. If I had just x, that's a 1-degree polynomial. That's a linear, right? If I just had the first 3 trinomials here, that's a quadratic, and therefore it's a 2nd-degree polynomial. All right. I don't know. What do you mean? No, which part? Like I don't know what information. Be more specific. Okay. They're usually written in standard form, beginning with the non-zero term of the highest degree, and then descends on from there. So for example, here, if I just have a polynomial function, it's going to have a leading term. The leading term can be positive or negative. So this is my leading coefficient. And the leading coefficient is with the term that has the highest power. Yeah, the leading coefficient is with the term that has the highest power. It is the, however you want to put it. Okay. So even if it's not even if it's not in standard form, should I be able to identify my leading coefficient? Yes, because I will look for the term that has the highest power. Okay. So breaking it down, summarizing all those fancy words. So for example, we have this polynomial right here. When we look at this polynomial, we know that it's a poly, not a tri or a bi or a mono, because there's more than 3 terms. Does that make sense? Okay. The leading coefficient is with the highest exponent. And the degree here is what? 3. So this is a 3rd-degree polynomial. Which is why it's called a cubic function. Does that make sense? Okay. The number that has no variable is your constant. The number that has a power of 1, that's your linear term. The number that has a power of 2 is your quadratic term. And then you have your cubic term. And technically you have your quartic, your quintic, your heptic, your heptic. And there you can continue with the names, but not necessary. All right. Question about standard form and the parts of the polynomial function. Cool. All right, so classifying again, just breaking down a little more. Here, if I asked you what type of polynomial this is, it's in standard form because it's only, it's a monomial. And its highest degree is 4. So therefore, this is a 4th-degree monomial. Yes. All right, here, I have this polynomial. It is not in standard form. So when I write it in standard form, my leading term has the highest power. That highest power lets me know that it is a second degree polynomial. And there are 3 terms being added together, so this is a trinomial. Okay, last one we have here to analyze is it's not in standard form because my leading term is not my highest power. So I put it in standard form. My highest power is 5. So this is a 5th degree polynomial. And there's only 2 things being added together, so it can be classified as a binomial. Does seeing it like this help? Clarify, bring back some thoughts? All right, so we're going to go through and we're going to classify. We're going to determine whether it's a polynomial, state its degree, state the number of terms, and identify the leading coefficient. All right, so here is P of X a polynomial? P of X is a polynomial, right? So it is, and it, to be more specific, it's a what? And why is it a trinomial? There's 3 terms. And what's the degree of this trinomial? It's a 3rd degree. And what is my leading coefficient? 4. And then this guy is my constant. Cool? All right, f of x. So is f of x a polynomial? Yes. What, to be more specific, what is it? A trinomial. And is it written in standard form? No. So we're going to rewrite this. So to rewrite f of x, it would be negative 5x to the 4 plus x plus 3. So we have a 4th degree trinomial. I don't know why I did that. I'm just gonna let it roll. Here's my leading coefficient, and here is my constant. Is g of x a polynomial? It's not. It's a cube root. Is that not a cube root? Yeah. It's a, no, it's not a polynomial. You're not going to classify it. You can't classify it if it's not a polynomial. It's a single term with a power greater than 1, equal to or greater than 1. So this would be g of x equals x to the 1/3. And that power is not greater than or equal to 1. So you're not even going to classify it because it's not a polynomial to begin with. It's a cube root function. Yes, polynomial.
So then the other g of x would be.
This would be a monomial. So big G of x is a 0 degree monomial. Yeah, I mean, there's nothing there. It's just a number. A constant is just a 0 degree. This is not even, but first off, is it a polynomial? Is this a polynomial? Yeah. So if the answer is no to be a polynomial, you're not even going to classify it anymore. So it's a no, so you're done and you keep it pushing. And why is it not? Because it's a cube root. Okay, here, h of x, is it a polynomial? H of x is a no. This is a rational function. How do I know it's a rational function? This guy. Rational means you have a variable in the denominator. So thinking about our parent functions, this is a rational function because there's a variable in the denominator. So therefore, I can't classify it as a polynomial because it's not even a polynomial. Okay. H of x, is it a polynomial? Yes, it's a polynomial. Is it in standard form though? No. So we would have to get this in standard form. In order to get this in standard form, we would have to FOIL. And if we FOIL the first one, we get x squared minus 6x plus 9. And then we would have to distribute. And that gives us negative x to the 5th. Minus, well, the negative times a negative is a positive, sorry. 6x to the 4th minus 9x to the 3rd. Because you would FOIL, then distribute this guy. So what is the degree here? 5th. And I can classify it as a trinomial. So the hint here is when you have two polynomials being multiplied, to find their degree, you just add their highest powers. What's 3 plus 2? And what did we come out to be? A 5th degree. When you are multiplying two polynomials to find their degree, you're just adding the highest powers. So 3 plus 2 makes this a 5th degree polynomial. And a one variable is a function of the form. There's the definition. Where these are constants. So your an minus 1, they're your constants called coefficients. And n is greater than or equal to 0. I did. I said what makes it a polynomial is that you have a constant linear quadratic term or more, and it just continues. A polynomial can just be one term. They're all called polynomials, but then you can specify.
Pardon this interruption. Teachers, students should all be back in their classrooms now. The cafeteria is empty, so it's time to take attendance. Thank you.
And then we did some examples of polynomials. So classifying them, we can further classify them by their degree and their type. The polynomial is the branch, the umbrella of it all. And then you can classify by degree, leading coefficient, by type, but everything is a polynomial. A constant, that's why right here, a constant is a polynomial. A linear is a polynomial. A quadratic is a polynomial. As long as n is greater than or equal to 0. That's a no, because your n is 1/3. Right? It's a radical. And just knowing your parent functions, this is a radical altogether. All right, so here we have negative x cubed times x squared minus 3 squared. And so in case y'all wanted me to do it again or had enough room, I put it on a separate page, but if we're okay, then this one on h of x, I added in case someone needed it to be further explained. Or are we okay with it? No, we've already did it. I'm saying we just, do y'all need me to further explain or do you understand what happened in that little box?
Oh, no, I understand.
Okay. All right, so polynomials. What separates polynomial functions also is that their functions themselves, the graphs, are smooth and continuous, okay? There's no gaps, no breaks, or holes in a polynomial. They're smooth and continuous. So if you look at graph A, notice how I travel along just all willy-nilly up and down. However, at any point, does my graph separate? Unlike if you look at graph B, these are all the different types of discontinuities that take place. You could have a sharp corner, a cusp, a gap, a hole, but none of this will take place ever when you graph a polynomial. It will always be smooth and continuous.
But isn't that like,
So up until this point, you've learned about polynomials. You've done constant, you've done linear, you've done quadratic, you've done cubic. Those are all examples of polynomials.
So is that why the rational function isn't?
Because it creates discontinuities and it's not smooth and continuous. Okay, now, a monomial polynomial where n is greater than 0, so not a constant, we just call that a power function. So if you just have f of x equals ax to the n, we call those power functions. So if it's a monomial polynomial that's non-constant, we call that a power function. So for example, if I had f of x equals 2x squared, we would call this a power function. Does that make sense? Because it's a monomial and n is greater than 0. Yeah. If I had 5x to the 100, this would still be a power function because it's a monomial and n is greater than 0. Okay, there are two types of power functions. You have your even power functions and your odd power functions. These are the characteristics of the even power function. So my even power function, going back to your parent functions, the first power function you learn is x squared, the quadratic. And when you think about the graph of x squared, what things do you notice? Well, the function is symmetrical with the y-axis, right? The domain is all real numbers. And the points -1, 0, 0, and 1, 0 are always on the graph of the parent function, right? Yes, all facts, all things that we've known since Algebra 1. Okay, in addition to that, as the exponent increases, so when I go from being a square to a 4 to a 6 to an 8, what's going to happen is that the bottom's going to flatten out. So when I graph f of x equals x to the 4, it's still going to have all those other properties, but it's going to be a little flatter at the bottom. Pretend that I'm drawing this as evenly as possible. Don't worry, I have pictures. I said, don't worry, I have pictures. So don't worry. All right. So as we look here, the end behavior of even functions are going to be doing the same thing. No matter what it is, if it's an even function, the end behaviors are even. They're doing the same thing. So if on the left hand, I'm going to positive infinity, on the right hand, I'm also going to be going to positive infinity. We have even behaviors, even function, even behaviors. Make sense? Okay. Now we're going to talk about the odd. The first odd power function you learn is the cubic. F of x equals x to the 3rd. The cubic function, it goes through the origin and it has origin symmetry. What that means is it's rotational around the origin, right? Remember, that's the one, if we turn it upside down, it's going to look exactly the same. So it has origin symmetry. Domain is all real numbers. And the points that are always on there are going to be -1, 1, 0, 0, and 1, 1. My negative one didn't make it. It should be -1, -1. Okay. Its end behavior, same thing as in a flatten, by the way, but its end behavior are opposite. Think about odd opposite behaviors. If I am heading to negative infinity on one end. On the other end, I have to be heading to positive infinity. Odd behaviors for odd powers. Does that make sense? Odd behaviors, odd powers. So this is saying as x goes to positive infinity, y goes to negative infinity. And then as x goes to negative infinity, what does y do? It also goes to negative infinity because they do opposite behaviors. So let's look at the graphs of these. Bam. So when you look here, notice how with x squared, it's a little more curved. When I become x to the fourth, what happens? It got a little wider, it starts to flatten out. Okay. Over here, x to the third, a little curvier. X to the fifth, what did it do? Starting to flat out. Okay, that's what it means that as the n gets greater, the graph gets flatter around the origin. And then look at their behaviors. Notice how even functions have even behaviors. I'm going to infinity. Oh, I'm going to infinity too. Oh, and odd functions have opposite behaviors. Oh, I'm going to negative infinity. Oh, don't worry, I'm going to positive infinity. They have opposite behaviors. Okay. How do we feel?
Are there gonna be like graph questions that's like, is this odd or even?
Oh, your homework, but out of the test.
Wow.
So that you can make sure you understand the premise of them. Because it's needed for foundational understanding. All right. Other thing with power functions is transformations. Can you move the graph and explain the movement of the graph? Has this transformation list changed in 2 years? No, it's the same transformation rules.
Did I can't like copy that down?
On your note card? I don't care what you put on your note card. Okay, this never changes, and I use this every year, show you, and every unit that involves transformation, you see the same transformation rules. I don't change it. Why? Because they don't change, guys. All right. So if I'm adding to the function or subtracting to the function, that's going to cause me to go up and down. If I'm adding or subtracting to the x value, that's going to cause me to go left or right. And remember, my x is a liar. X is a liar. Okay. If I have a negative on the outside of my function, it's a reflection over the x-axis. If I have a negative with my x, it's a reflection over the y-axis. If I multiply, I'm going to stretch or compress if it's affecting the y. If I am multiplying the x, it's the opposite. I'm going to compress or I'm going to stretch. Here you can see how it affects the ordered pairs. Anything new there? Not at all. So for example, if we have the power function or this polynomial, 1 minus x squared. First off, it's not in standard form. We're going to put it in standard form. F of x equals negative x to the 7 plus 1. So we have a 7th degree binomial. Agreed? Yeah? All right. And we talked about it's an odd function. How do I know it's odd? That's 7. And if I'm odd, that means that what's changing is my behaviors are going to be opposite, right? They're going to always be opposites. So I'm going through the origin first off, initially. But what does that 1 tells me? Instead of going through the origin, what's going to happen? I'm going to go up 1. So no longer am I at the origin, I'm at 1. Does anything else change? Yes. What does this negative tell me? So instead of heading like this, it's going to be doing what? I can't. Okay, that didn't go very well. That looks like an H. I tried to make it the other way. Oh my gosh. You see what I tried to do? I can't make it curve. I can't curve.
There you go.
No, why?
That's really why.
At least it's not on the graph yet.
Oh, why do you go up? Yeah, don't go up.
Okay, hold on.
Yeah.
There it is.
Yay.
Okay. That was a lot of struggle there.
It's like how that's us in math.
That was a lot of struggle, and I don't know why that was so difficult. All right, I'm gonna do it this way. Because it's a 7, we know it's gonna be flatter, right? So it's a 7, so I'm just gonna draw the flatness out and then try to do my curves from there.
Oh my God.
Pretend I can't go any further. I can't go any further. I don't trust the process. Close enough. I think I did it. Flatten.
Good job.
There we go. It's close. All right, it flattened because it's 7, right? So it gets flatter. We are now decreasing instead of increasing because of that negative, right? And we shifted up 1. That's our sketch. Good enough sketch?
So odd numbers, they get flattened.
As the number gets bigger, remember it said it flattens around the origin. So as our power increases, it's going to flatten. All right. Notice I don't have anything numbered, so it's just to make sure it's a sketchy sketch. All right, let's try another one. This one has a lot of things happening. So we're talking about transformations here. 1, what does this guy tell me? My X is a liar. My X is a liar. So we went left 1. So we're shifting left 1. And then we have a vertical compression. By a half, right? So here, X plus 1 to the 6. It would have been, I would have been at the origin, right? But I've shifted to the left 1. And I'm at vertical compression, which means that I'm going to naturally go out wider, right? So I'm going to get wider. So I'm flattened out here. I'm going to do my best, guys, on this flatten out business. Got to flatten out. And then I'm going to curve a little more. I got to do it in parts. That's the trick. What? I concentrated. That's all I got.
That's it?
No, it froze. It doesn't look like that on my computer. I was like, it froze. I don't know why. I have it all the way drawn. I promise. Look, it's a break in the internet connection. I promise it's all the way on my computer. It is, right? It's all the way on my computer. Quickly.